Hello and welcome to our webinar on contribution analysis with counterfactuals. My name is Stefan Conradi and I will be your host today. I'm very excited that this topic has generated so much interest. By now, I think we have almost 200 registrations for this webinar. In fact, almost 250 registrations. So thank you very much for joining me today. Let me start off by introducing you to today's agenda. We'll start off by talking about motivation in terms of how do causes contribute to observed outcomes. It's really a very old question that we are considering here, and we'll see how this has been raised by some very famous marketers of the past. This brings us to our objective. We wish to determine the proportional contributions of causes towards outcomes, all from observational data. So for that, we need to take quite a number of steps. And one of the central ideas is that we need to calculate such contributions with counterfactuals. But first, before we can calculate contributions, we really need to infer these counterfactuals first with a causal model. So that's the central concept. That I want to illustrate with our contribution analysis workflow. So I think this whole process is best illustrated with a practical example. So what we're going to do, we're going to define an arbitrary data generating process, really just a fictional world of which we know all the elements. And from that, we produce data, which we can then subsequently use to learn a Bayesian network. And from that with that Bayesian network, we can do a whole lot of things. And most importantly, by making causal assumptions, we can infer outcomes based on counterfactual conditions. This is precisely what we need. Getting these counterfactual outcomes, because with that, in the remainder of this workflow, we can then calculate contributions. And as you will see, there are many twists that we need to take into account: type 1 versus type 2 contributions, model-based versus data-based, baseline contributions. We can even take this further to talk about synergies and temporal decompositions. Depending on how much time we have, we will get to these last two bullet points or not. But we'll have to see. It's going to be a very, very, very full presentation today. So, of course, BayesiaLab 8 is the product that you will see in action here. And as you may know, BayesiaLab is just part of a fairly comprehensive ecosystem, including desktop software, web applications, and APIs. But as I said, today is really just all about BayesiaLab Professional. That will focus on that itself. In the chat panel, I've already seen a few questions. One of them being, can we get the slides? Yes, of course, you can get the slides, the networks we develop, plus the video will be available afterwards. So by the end of today or tomorrow, you will receive a link to the video and all the other materials. So let me talk about motivation for a moment. Calculating contributions. That's really what we want to do today. And this is not at all even though it sounds like a very simple question, it's a very innocuous term, and it doesn't sound like a terribly ambitious task for a sort of an analytic project. However, it's probably a lot more challenging than you would expect. Let's start off with one of my most favorite quotes, and that is, "I know I waste half of my advertising dollars. I just wish I knew which half." This quote has been attributed to John Wanamaker, Henry Ford, J.C. Penney, and actually several others. what they are saying is that they don't know which of their advertising contributes to sales. Apparently, they were unable to calculate their contributions. But you may say, well, it's really quite a straightforward concept. After all, contribution, the way we colloquially talk about it, is merely the sum of all the sources. If we think about donations, just the individual donations add up to 100% to a grand total, and then each contributor is that proportion of the total. Very straightforward. However, when we look at this in the marketing context, it's a little different. So let's look at this conceptual diagram that describes qualitatively how marketing and advertising may contribute to sales. First of all, to start off at the very left, our marketing decisions determine the resources and the marketing mix that we're putting into the system. That determines what exactly we do and how many resources we spend. In that sense, we're certainly contributing, but this is not necessarily contributing in the same way to the desired outcome in terms of sales. So the issue is that we have, of course, a consumer who may or may not perceive and act upon the promotions as we would hope. Hence, some marketing activities are literally wasted. Also, the marketing efforts that are effective may not yield results that are proportional to the efforts we put in. We may spend, for instance, a little on internet advertising and have great results. On the other hand, we may spend a lot on TV and only have moderate success. Plus, there is perhaps a baseline demand which exists regardless of our current promotions. So what we are interested in are the contribution towards the outcome, what actually contributes to sales. Now, the big challenge here is, or what we really need to point out, that the flow of what happens inside the consumer's head, the interactions with the consumer's understanding of the brand and so on, and perhaps competitive advertising, etc., that is not visible to us. We cannot see that. We do not know what exactly is happening here. We merely have a theoretical representation of what may happen inside the customer's head. So, and for that reason, it's really not observable. The quantities that we are interested in, the contributions, as these contributions flow toward the outcome, we cannot directly observe, and that's exactly what Wanamaker, Ford, and Penny have stated over 100 years ago. So, what are we going to do? Well, let me rephrase it, or let me now translate that into our objective. And I want to be very explicit here. We want to now learn how the marketing drivers and the baseline demand contribute to sales. These flows we want to understand and precisely understand the proportions in which they contribute towards sales. So our objective is to run a contribution analysis that takes what is not observable and decomposes that we go from what is not observable, what we cannot see, what we can only understand theoretically, and translate that into, or decompose that and recover these contribution streams. So that's our objective for today. Now, I should point out kind of a potential confusion risk, and this is based on my experience in having conversations with market researchers, marketing executives, because quite often people think of contributions as a different term for effect size. But it's very important to make a distinction here, as we will. So yeah, let me give you an example. Effect sizes are really forward-looking quantities, representing the capability of a cause when invoked to bring about an outcome. So I could, for instance, say, at a speed of 2000 RPM, my car's engine will produce 700 Newton meters of torque. So that's very important to me, for instance. So that is forward-looking. If I were to do this, then the engine would deliver. Contribution, on the other hand, are backward-looking. I am decomposing an outcome and attributing it proportionately to multiple causes. You may have heard quotes like, success is 80% attitude and 20% aptitude. So you're looking at the outcome, success, and then look back where it came from, what contributed to it. Or in a more legal context, you may say technical malfunction and human negligence were equal contributors towards an accident. For instance, in litigation, trying to establish liability. Of course, so let's just bear this in mind, the difference between effect size and contributions. However, what we will see is that in order to get to contributions, we need to understand effect sizes. However, having effect sizes alone do not necessarily give us contributions. But we'll talk about this more throughout the next 45 minutes. Okay. Now, this concept could just as well apply to many other potential domains. I already touched on kind of a legal reasoning about liability. Of course, you could apply this to policy analysis, public health. Just think about, and this is a very, very common question, looking at health conditions that are observed in the population and then attributing those conditions to different causes, lifestyles, risk factors, etc. So it's really looking for what is responsible in what proportion. All right. Let's now return to our marketing domain again. And as it turns out, estimating even a single contribution is already quite difficult. I started really thinking about this concept of contribution in all seriousness back in 2012 or so. At the time, Michael Dell asked his analytics team the following question: what sales did we generate with the money we spent on the advertising campaign? They had just run an advertising campaign and they felt the result was great. But what he was really referring to was contribution. He wanted to know, how did the $1 million or so that we spent on advertising contribute to sales? And to answer his question, we really need to employ a concept that you may not have heard of before in analytics. And that is the concept of counterfactuals. Unfortunately, the term has some negative connotations that are implied by all these synonyms: false, incorrect, made up, truthless, untrue, untruthful, wrong. And in that sense, counterfactual is often interpreted as fictional or even surreal. But that's not where we're going with this. Rather, what we want to do with counterfactual is looking at counterfactuals as possibilities or courses of action that were not chosen but could have been chosen. So for instance, I could have turned left when I actually turned right, or I could have scheduled this webinar for tomorrow, but we're doing it today. In that sense, these counterfactuals are not just possibilities, but very realistic alternatives. And against that notion of counterfactuals, I now want to rephrase Michael Dell's earlier question. What I think he is really saying is he's trying to establish the difference between the sales that occurred given that we ran the advertising campaign spending X dollars and sales had we not run the advertising campaign, meaning that we spent $0. The former is factual, the latter is counterfactual. He is trying to get the answer to what is the difference between the two. And of course, the challenge is that the latter, the counterfactual, is not observable. It didn't happen. We can't measure what in fact did not happen. So we're trying to use that difference between the factual and the counterfactual to define contributions. And I'm introducing another term here, decomposition, which really is the measure or the difference between the actual outcome and the counterfactual outcome. What we actually did, the outcome based on what we actually did, minus the outcome, the counterfactual outcome, had we done X equals 0 instead. And here I need to emphasize done, not just merely observe, but had we actively set X to 0. And so with this decomposition now, we can divide decomposition by the actual sales. And with that, we arrive at the contribution as a kind of as a percentage of the overall outcome. Now, what I need to stress here is this is what we will call the type 1 contribution. Later on, we will also talk about a type 2 contribution, etc. So there are many kind of angles to this. But for now, this gives you a basic sense of what we're talking about in terms of contribution. So you may obviously ask the question now, well, how can we know that? How can we establish sales given if we had not run the advertising campaign? And which leads to the question, can we somehow calculate this counterfactual sales volume? And this is clearly a causal question. And we could answer this causal question if we had a causal model and were able to simulate a counterfactual condition, such as we do X equals 0. We set X to 0, we spend $0 on advertising. Okay, so can we build a causal model is our next question. And you can see I'm kind of peeling back the onion further and further. So if one question leads to the next question, so we'll actually have to step through quite a few layers here until we get to the answer. So can we build a causal model? Now, what we can certainly do very easily is establish an association or correlation between advertising and sales. We can certainly measure what we do in advertising. After all, we probably know what we spend on different channels, TV, online, print advertising, etc. And then presumably we also know how much we sell. We record that. And so we can, over time, establish associations. Very, very straightforward. But of course, that is not enough. Associations are not what we need. We need a causal model. So what are we going to do? Let me now take you to our map of analytic modeling and reasoning. And if you've read our book or seen some of the previous webinars, you've probably seen this diagram several times. What this shows is on the x-axis the purpose of an analytic model. And here on the left, we have association correlation. And on the right, we have causation. Those are the two principal purposes that a model can have. Predicting on the left and inferring causal interventions on the right. second question, or the second axis here on this map of analytic modeling, is the y-axis, where we show where models can come from. At the top, we have data. Models can just be generated from data without having any theoretical knowledge, or alternatively, models can be built based on theory in terms of how we are specifying them and thinking about how the world works, and we can encode that in a functional form or a structural equation model or something like that. Now, if we now position the concept of predictive models onto this map, then I would argue this belongs in the upper left-hand corner. For predictive models, we can learn quite easily from data, and pretty much any association correlation represents a predictive model. But what I'm emphasizing here is, given that we're observing X, taking on a value, and based on that, we can predict an outcome. As opposed to what we are after here, our target is we want to infer given that we do. So this box is here on the right-hand side, on the causal side, and it is positioned further down because what is not possible is to generate a causal model just from data. With a causal model, and here I'm emphasizing the do X, we are actively setting X to a value of our choice. So how do we get there? What we have is correlation association. That's very easily to establish from the data from any such domain. What we need really is going the path of theory. We need to introduce, in addition to what we can discover through machine learning in terms of association, correlation, we need to introduce our theoretical domain knowledge to get from an observational predictive model to a causal model. Now that is actually not as easy as it sounds, and we'll see what stumbling blocks may exist and also what tricks are out there to make that process a little bit easier. But we have to make assumptions, and our own human assumptions are potentially wrong. So we need to be careful. This is not something we can do on autopilot. Anyway, we're going to use the framework of Bayesian networks to do this. Bayesian networks are incredibly helpful in this context because many of the assumptions that we need to make can be very nicely represented there. It becomes so much more straightforward and intuitive when we represent such problem domains as Bayesian networks. We really make our life much easier that way. So, but as we now go through these analysis steps and contribution calculation, I think it's best to showcase them with an actual example. And I'm trying to keep that example very, very simple, if you will, a toy example. That's not particularly realistic, but quite simple so that we can really focus on the steps of the workflow as opposed to getting just confused by a too complex structure. Anyway, so here is our example. This is a fictional world that we've just created by fiat. We just said, okay, this is it. This is how the world works. We have a system, a domain, where we have a variable y that is caused by x1 times x2 plus x3. So we know exactly from this formula how the variables x contribute to the outcome y. We also know the distributions of these variables. They are all the values of these variables are all drawn from these distributions. And the exact nature of these distributions, that doesn't matter really. We're simply using this to create some synthetic data, which we can then subsequently analyze. But please note, we're saying here x1, x2, x3 are causing y. This is not just a mere equality. Anyway, we're producing 5,000 observations. That produces our synthetic data set with x1, x2, x3 as drivers, or we may say refer to them as causes, and y being the outcome. So that's our synthetic data set. And now that we have the data set, we'll erase everything we know about the data generating process, except the knowledge, the domain knowledge that the x's are the causes and the y is the effect. So we're now taking this data set, and this is actually a very typical starting point with plenty of data, but little knowledge of the data generating process. Our objective now is, based on the data, to estimate the contributions of the drivers x1, x2, x3. And we want to do this entire contribution analysis with Bayesian networks and with our software BayesiaLab. So let me now share with you how I'm going to structure the remainder of the presentation. I will first give you a quick preview of what the final product will look like. And we can breeze through this final process in just a few seconds, and we'll almost instantly get to our results, which is really cool, but it doesn't point out what is actually happening behind the scenes. And this is very important to understand. While in the end, we will be able to get a contribution analysis report with the click of a button, here in this webinar, we really need to spell out what exactly is happening here. So, but first, let me take you very quickly through the screenshots of the workflow, and then we go back and review the individual steps that are happening. So with this data set in BayesiaLab, we will go through the data import wizard, define the types of variables we have. In this case, these are all continuous variables. This is a very easy data set for us because there are no missing values, so we don't need to do any missing values processing. What we do need to do is discretization. I will not spend any time discussing that here, but given that we have a very large or fairly large data set with 5,000 observations, that's not much of an issue or concern. So with that, we conclude the data import wizard and get to our initial unconnected Bayesian network. We will start learning. In this case, we want to learn a supervised model, or want to use a supervised learning algorithm, which now, here in this case, we're using a Markov blanket learning, which now gives us a model that relates the target variable y to our drivers x1, x2, x3. And by switching into the validation mode, we can now see how all variables are distributed. Specifically here, we're looking at the monitor panel, which gives us quite a bit of information on the nature of the distribution of the variable, the mean values, standard deviations, and so on. This will become very important for us as we look at the step-by-step analysis. But for now, we could simply, if we were just to jump to the conclusion, we could simply click contributions and now get all the contributions that we are interested in. We can go straight to the contribution analysis report. It's simply a single click away when we hit that contribution button. So, or let me rephrase that. Once we have our network, once we've imported our data, learned the network, and later on, I'll add some caveats about that we need to make sure that this is a good network, it's validated, etc. Then we can click contributions and get the decomposition that we were talking about. So, but now, of course, you may say this is great, But what we just saw, was that even a proper causal model? Because this model that we have here, that we see in our screen right now, really doesn't look or doesn't seem to relate to what we just talked about, because we just restated and said x1, x2, x3 cause the outcome y. But that is not indicated here with the arcs as we see them here. So no, that is not a correct causal model. That is not in sync what we believe is the case from our data generating process. So where are we going with this here? Well, while it is not a causal model, this network, as we've learned it here, is still an approximation of the joint probability distribution of the underlying data. And as it turns out, even this network as we see it here is non-causal. We can still use it for causal inference. And you may say, well, how is that possible? Well, what we need to do is we need to condition on the correct confounders, which leads to the question, well, how do we determine and which ones are the confounders? And there is, in fact, a criterion that can help us to identify them very easily and quickly. And that is what is known as the disjunctive cause criterion, first proposed by van der Waele and Spitzer in 2011. It's a very, very simple criterion that says we propose that control be made for any pre-treatment covariate that is either a cause of treatment or of the outcome or both. And what we additionally need to assume that there are no unobserved confounders. And I'll repeat this a few more times throughout the rest of this webinar. This is very important. Anyway, once we have identified the confounders as per this criterion, we can then use our non-causal Bayesian network very easily for causal inference. More specifically, we will use what's called direct effects analysis and likelihood matching. That is very, very convenient, and one of the reasons why I like Bayesian networks for this approach. Now you may say, hey, couldn't we have created a real causal model like this one here? This would represent the domain as we know it. Well, yes, we could. We could have done this. In the simple case, we might be able just to say, we know the causal direction. I'm still using kind of the more, not elaborate approach, but the approach based on a non-causal Bayesian network, simply because there are many domains, many problem domains where the relationships are too complex for a domain expert to really know how all the causes might relate to each other. So quite often it is not possible to establish causal directions for all variables, and therefore it is easier to machine learn a non-causal Bayesian network and then apply this disjunctive cause criterion for confounder selection. So that is the theory, the causal theory that now goes into our model. Through the selection of confounders, we now get to a causal model. Now we can do what we're looking for. Now we can simulate counterfactual interventions on any of the x variables to infer the individual causal effects on y. So now we can answer the questions such as, what would have been the value of y had x1 not been at the factual level, but had we set it to a counterfactual level, x1 equals 0. So let's do that. Let's do that in BayesiaLab. It turns out to be very simple what we need to do, and now we're focusing here on the monitor panel. As per the disjunctive, and we'll start here with variable x1. For x2 and x3, it would be exactly the same process. But if we now take into account the disjunctive cause criterion, this says what we need to do, we need to condition on confounder x2, confounder x3, and to infer the causal effect, we have to set x1 to 0. Now, how is that done technically? How can we condition on such a distribution? In BayesiaLab, it is actually very simple because we can employ BayesiaLab's likelihood matching algorithm to fix the probabilities or the probability distributions of the confounders. So here on the left, on the left panel, you see x2 and x3 with their marginal distributions. By clicking fix probabilities, we basically lock in those distributions, we condition on them, and with that we can now compute the counterfactual inference. We can set x to 0, the counterfactual condition, and then read out the inferred distribution of y, and we can specifically look at that value. And now that new value, I think it was like 50.0 or whatever it was, now the new value with x1 being set to 0, this driver being removed, we're now at 27.5. So that's the decomposition we are really looking for. We're trying to compare our marginal distributions to the counterfactual condition. And so here in this case, the difference is the difference between the counterfactual value of y and the factual value of y is 22.8. And this is what we can now use to calculate the contribution. I know all this is very verbose and with many terms, but ultimately it's very, very simple. And as I pointed out earlier, later on when you actually do this, it's just a click of one button. We're just going through this once to really see what is happening. So anyway, we have the decomposition between the factual and the counterfactual outcome. We divide that by the factual outcome, and therefore we can now say the contribution of x1 is 45%. Of course, you may say, is this really the only way to look at the contribution? In fact, there are other ways of looking at it. We could now say, not what's the difference with the situation when we take x1 away, but what if it were only x1? So if x1 were at its natural observed level, but if x2 and x3 were at counterfactual levels, like if they were at their lowest possible state, which leads to yet another question. I keep peeling this onion here, because we need to now question what is the counterfactual state of x3, because x3, when we look at this distribution, never has a value of 0. The lowest observed value is like around 15. So how can we now, what is counterfactual here? Well, by default, most often we use 0 as the counterfactual states, but there could really be many counterfactual states, anything other than what actually occurred. And what the correct neutral state is really entirely depends on domain knowledge. What do we know about this domain? What is the correct neutral state and the correct counterfactual state? Quite often it's simply 0, absence, average, default, minimum, standard, least possible, and so on. But what it is really depends on our domain knowledge. Perhaps this is an appropriate example right now with the heat wave in Europe. Beer distributors may wish to estimate what is the contribution of the heat wave on beer sales. And so temperature is clearly a driver. But now And the actual temperature, we can very easily establish. We can just say, well, right now it is 35 degrees Celsius. But the neutral state, the counterfactual state, should probably not be 0 degrees Celsius or 0 degrees Fahrenheit or 0 degrees Kelvin. That makes absolutely no sense. Perhaps the neutral counterfactual state should be the typical temperature at this time of year. So perhaps it's like 25 degrees Celsius. That would be the historical average. And that's what we should use as the counterfactual state in contrast to what it is today. Now in BayesiaLab, we can specify that. So if it's not, by default, BayesiaLab picks the lowest numerical value as the neutral state, but we can choose anything we want. This is especially important when we use categorical variables, like where the neutral state is blue as opposed to green, yellow, purple, what have you. Then we can specify that in the node editor and check the box for reference state. Okay, so let's look at this. Let's look at this type 2 decomposition. And this is really about contributing or calculating what if x1 were the only active variable, everything else were basically at the minimum level. So that's what our left and right panels here compare. At the left, everything is minimum, and then on the right, we have x1 taking on its factual distribution, while the remaining variables remain at the minimum level. And so with that, we again have a decomposition. With that, we can calculate the contribution, what we call type 2. So this is the difference, type 1 and type 2 contribution. And these numerical values may seem different to you, like with 45% versus 1.9%. So what is the actual contribution here? There is actually more. There are more angles, and you'll see how we try to be very careful or very systematic about capturing all possible angles as to how this contribution can be calculated to really get to a solid estimate that makes sense from all perspective. So far, we've just taken the entire model, we've taken the entire network, and predicted the counterfactual outcomes or inferred the counterfactual outcomes. Now we're looking at this at the record level of our data. So instead of inferring with the model as a whole, we're now going into each record and comparing what we observe, the factual state, with the counterfactual state. Here in this case, for type 1, we set our driver x1 to 0 for observation 1, then for observation 2, observation 3, and so on, leaving x2 and x3 at the factual states. And then we compare that, the left and the right panel, with each other, and thus arrive again at a contribution. We call this contribution type 1 based on data. We can do the same again, this time making x1 the only factual driver, with everything else being at the counterfactual state, and so on. You can see this is really, there are a lot of steps, each in itself quite simple and straightforward, but it's easy to lose track of where you are. And there is more yet, because there's also a baseline. Because so far we only compared the presence and the absence of the drivers, but we could now also ask a question, what if all drivers were absent? All x1, x2, x3 were at the minimum level, which we can then consider as a baseline condition. Basically, we do absolutely nothing, no marketing, no promotion, nothing. How much would we just sell based on latent demand? So we can compute this at the model level. And we can again compute this at the data level, where we simulate this for every individual record. And by now you can really see how this is quite tedious if you have to word this manually or even in a spreadsheet. So in BayesiaLab, once you have your model, BayesiaLab can calculate this for you automatically and report all the decompositions and contributions in this convenient table. And in the leftmost column, you get the mean contribution that tells you what the average is of all the contributions we have calculated. Plus, in the top row with the blue background, there we get the baseline. So now, looking at the data as we have it, we can now say from x1, given the observed values, x1, and you can see it's very easy to get sort of mixed up in terminology and so on. X1 provides 21.38% of values towards Y, X2 the same amount, X3 just around 8%. And the baseline value of Y is 48% of its average value. So this is this answers the question of looking back. So we have now decomposed all the drivers contribute to sales, or in our case, we've just used this hypothetical example, but translating this back to our marketing domain, we can now decompose and go back from our actual, or let me rephrase that. The contribution analysis now gives us what is not directly observable in terms of what is happening in the consumer, but we can decompose now which driver, which marketing driver, or which driver or cause in general contributes toward the outcome, in our case, sales. So the report really summarizes this at the click of a button, makes this problem appear very easy and very convenient for the analyst to resolve, and delivering quite impressive results practically instantly. But here I need to add a warning of some very important caveats, and that is, because it is so easy to get a comprehensive contribution report, it is also quite easy to quickly report incorrect results. So before you click that button, you really need to make sure that the model that you have machine learned is correct, that you have validated this. We have omitted those steps today for lack of time. You need to review the causal assumptions. You need to review what are the confounders in terms of applying the disjunctive cause criterion. You need to think about whether there could be any unobserved confounders. If there are, any results would be very, very heavily biased. You'd have to think about, or before you move to contribution, it is very helpful to review the causal effects for plausibility and review them with domain experts. So before you calculate your contributions, really think about, does this domain represent the world as we know it? Does this make sense? Is this plausible? And then, again, before we hit the button, we really need to know what's happening. We really need to know what is type 1, type 2, model-based contribution, data-based contribution, because otherwise it's very easy to get lost in all these numbers, and you run the risk that you're not reporting the correct results to the stakeholders. So with all the convenience and how easy and fast this contribution analysis is, you really need to know what is happening behind the scenes. So, in conclusion, and given the need to really know what's happening behind the scenes, I would very much like to encourage you to consider joining some of our courses. We're probably the world's largest provider of Bayesian network courses, seminars, and webinars. And perhaps you've already participated in some of our webinars or attended some of our live events. For topics like this that go a little bit deeper, I would very much recommend that you join one of our 3-day courses. The next one we have coming up in September in Paris, both an introductory and an advanced course back to back, followed by the same courses, introductory and advanced, in Durham, North Carolina, in the context of our annual conference. And what I should really need to point out, even the course that takes place in France will be conducted in English. In the past, some folks were hesitant to register for our course in Paris because they thought it would be in French. We do offer French courses as well, but these two will be conducted in English. So pretty much for anyone in Europe, those would be suitable. And as I just mentioned, we have our conference. Beyond the 2 courses, we have a two-day plenary sessions with presentations from users, from researchers, scientists who employ Bayesian networks to gain insight into different problem domains. A great way to learn about the broad spectrum of Bayesian network applications. And everything you've seen today, you can immediately try out. You can either download the demo version of BayesiaLab, which you can get straight away, or you can apply for an unrestricted 30-day evaluation version. And that I would actually recommend because our example today may exceed some of the limitations of the demo version. So, and one more thing, and this is something we very much encourage, we have an online community where you can post questions, for instance, about today's topic. There are lively discussions on all kinds of topics related to Bayesian networks and BayesiaLab. So I encourage you to log in or register first, log in, and join the discussion. And of course, beyond our community, our forum, I would encourage you to send any questions you may have directly to me. Here's my email address. I'm happy to connect with you on LinkedIn, on Facebook, etc. Please follow us on Twitter. I'd be very much looking forward to continuing or to carry on a conversation with you on contribution analysis or any other topic relating to Bayesian networks. So I see quite a number of questions were posted in the Q&A. We don't have enough time to address them right now, but questions and answers will all be posted in our community forum. So please take a look at that. Anyway, thank you so much for your interest. I really appreciate it, and I hope you will join us for one of our upcoming webinars and seminars. Thank you very much. Have a great day.